Hello, and welcome to Formulating Nanomedicines, Current Challenges and Solutions. I'm Scaleup, Field Application Scientist at Precision Nanosystems, Inc. Before I introduce our speaker, I'd like to thank you all for joining us for this webinar today. I'm happy to see this level of interest in this topic, one that we at Precision Nanosystems are very passionate about. Now, without further delay, it's my pleasure to introduce today's speaker, Dr. Gesine Heuck. Dr. Houk is a pharmacist with nearly a decade of experience in drug formulation and nanobiotechnology. She has in-depth knowledge of novel drug delivery systems and energy-activated prodrugs for cancer therapy and detection. She earned her PharmD from the University of Regensburg, Germany, and her PhD from the University of Geneva in Switzerland. And we've been fortunate to have her with us at Precision Nanosystems for the past 2 years. Before we begin the webinar, I have to cover a few basic housekeeping. First, if you have any technical issues, please type them into the question or chat box in the GoToWebinar window, and we will do our best to troubleshoot. Second, if you have any questions for our speaker, please use those same features and we will try to answer as many questions as possible at the end of the session. If we do not get to your question, we will answer all of them by email after the event. In today's talk, Dr. Houk will talk about the following challenges in nanomedicine formulation using several methods as examples and focusing on lipid-based nanoparticles. The first challenge is the rational design of nanomedicines. The next is the time required to make nanoparticle formulations. Then Dr. Houk will examine the reproducibility and scalability of existing methods. Now, without any further delay, it's my pleasure to hand the floor over to you, Gesine.
Thank you, Shell, for your kind introduction, and thanks for joining us, everyone. And I'd directly like to get this first webinar started with a quote. The limitations of current nanoparticle delivery technologies are substantial barriers to growth. So there are 3 points to make about this quote. First, it's not exactly a very positive one. Second, it's nearly 10 years old. And third, unfortunately, it still holds true. And the question now is, why is that? If we look at the nanoparticle development process, we start with the idea, the conceptual nanoparticle, followed by a development stage at the lab bench. Once we have a bench scale formulation that works, we need to find a way to make large batches of it and to use that in clinics and eventually get a commercializable nanomedicine product. Now, it is in the development stage and the transfer to large-scale production that we still need to overcome a number of hurdles. There is lack of control over the actual formation of particles at the molecular level, which makes rational design difficult. With the current methods, we still work in low throughput mode, as even though these methods have been optimized, they're inherently time-consuming. Then reproducibility is an ongoing issue. And for large-scale production, we either need to put a lot of effort into the process development, or, and unfortunately this is the case most of the time, the methods used in the early stage formulation development are just simply not scalable at all. So in the next slides, I would like to illustrate these challenges in more detail, and at the same time, I would like to present Precision Nanosystems' nanoassemble platform as a possible approach to address these challenges. For those who are not familiar with the nanoassembler platform, it consists of 2 products: the nanoassembler benchtop instrument for small-scale prototyping of nanoparticle formulations, and then the nanoassembler Scaleup system for large-scale nanoparticle production. And at the base of the platform, we have a disposable microfluidic cartridge that is used to perform a nanoprecipitation, or also called solvent displacement technique, to gain better control of the nanoparticle formation process. We'll look at all this in more detail further into the talk, but for now, maybe let's focus onto our challenges, starting with rational design. So what is rational design? From a nanomedicine perspective, we can define this term as the ability to predict the function of a nanoparticle based on its physicochemical properties. So in other words, if I can control the physicochemical properties of a nanoparticle formulation, and in its most basic form, this would be the particle size and the particle polydispersity, or the size polydispersity, So this would allow me to better predict the behavior of a nanoparticle formulation in cells and in vivo. This slide here shows the example of an experiment where nanoparticles of a different size were prepared. And this is what you can see here on the right-hand side. And these particles were then injected subcutaneously into mice, and their knockdown effect on a specific gene in the liver was tested. And so here the graph on the right-hand side shows the expression of the residual gene versus, so sorry, this is what we have on the y-axis, so versus the particle size of the respective particle formulations. And as you can see, it's not the very large, very small particles, but rather the particles of a specific intermediate size that are the most potent in knocking down this gene. So a specific nanoparticle size is needed to get the best in vivo effect. Now, going back to the challenge question, where is the problem with rational design and making nanoparticles? In fact, looking at our current nanoparticle formulation techniques, and this includes nanoprecipitation, we have actually very little control over the resulting particle size and size distributions in our formulations. And I like to use the beaker method as an example to illustrate this a bit more. Now, when we perform a nanoprecipitation in a beaker, we have a water-miscible organic solution containing the nanoparticle forming agent. So this could be a lipid dissolved in ethanol, for example. Now, this solution is added drop-wise to an aqueous buffer, for example, PBS. And this is done under constant stirring, usually with a magnetic stirring bar. Now, the change of polarity from the apolar organic solvent, so the ethanol, to the polar aqueous solution, which would be the buffer, this change allows the lipid to self-assemble into organized structures such as vesicles or micelles. Now, let's look in more detail at what happens when these two solvents mix in a beaker. First of all, we are in a turbulent mixing environment. Then we have a high solvent concentration gradient from the point of injection or the point of dripping of the organic solution into the aqueous phase and to the outside of the beaker, to the wall of the beaker. And this concentration gradient is poorly defined, or it has a poorly defined diffusion profile. Also, this concentration gradient changes the more organic solvent we add to the aqueous phase, and the higher the overall solvent concentration in the entire solution increases. Next, the mixing volume changes with each drop of the organic solution that is added to the beaker, which has an influence on the mixing time and the overall mixing profile in the beaker. And last, the mixing speed, besides being extremely difficult to control with a magnetic stirring bar, is actually fairly slow. And by slow here, I mean that we mix in the range of several seconds. Taken together, all these factors allow the lipids to assemble and reassemble in a pretty uncontrolled manner. And we have a very little control over the resulting size and the polydispersity of the nanoparticle population. So how can we get better in controlling this mixing and hence self-assembly process? This is where microfluidics come into play. So in microfluidics, we inject two miscible solutions. So this would be the ethanol solution with lipids and then the buffer. And so we inject these two solutions into a sub-millimeter sized channel under laminar flow conditions. So this means that the fluids will flow next to each other. And this is, in fact, shown here in this picture, only that instead of 2 solutions, we have, in fact, 7 solutions. And so they flow in this channel next to each other, and they only mix by diffusing into each other while migrating through this main channel. And since the channel has a very small diameter, the diffusion distances and the gradients are minimal. I can further embed structures so-called microfluidic mixers into the wall of the microfluidic channel. And these structures direct the fluid flows such that they fold over, as shown here on the left picture. And this folding over exponentially increases the interface between the two fluids while decreasing the diffusion distance. And as a result, the mixing speed is extremely fast. And here by extremely fast, I mean that we mix within millisecond range versus, if you remember what I just said before, mixing in a second range in a normal beaker. Also, since we bring the fluids together in an inline manner, the ratio of the two fluids to each other remains constant during the mixing. Now, the mixing speed is directly influenced by the flow rate or the flow speed of the fluids in the microfluidic channel. And at a millisecond level, this mixing speed actually dictates how the single lipids assemble into nanoparticles. In this example here, the lipid nanoparticles were formulated in the nanoassembler benchtop instrument using a microfluidic cartridge. And the resulting particle size, so the resulting particle diameter, was plotted against the total flow rate of the two fluids in the microfluidic channel. And as you can see, you can obtain a specific particle size by choosing the corresponding flow rate. We can obtain a similar effect by keeping the flow rate constant, but adjusting the ratio with which the aqueous and organic solvents are mixed. And in this graph here, we show the particle size of two liposome formulations as a function of the aqueous to organic fluid flow ratios. So one thing to observe is that the liposome formulation represented in blue contains a stiffer lipid, which is DSPC, and it has a natural tendency to form larger vesicles because of that stiff lipid. And the liposome formulation marked in green here, the lower liposome formulation, contains a more flexible lipid, the POPC lipid, that has a tendency to form smaller particles. So if I was making these liposome formulations in a beaker, I would actually get liposomes of one size with a relatively high polydispersity. But by controlling the liposome self-assembly through defined microfluidic mixing parameters, I can make liposomes of different sizes with low polydispersity. And so let's say I want to compare these two formulations in an in vivo model. Then I would want to compare vesicles of the same size. So here I would choose the lipid formulation with the flexible lipid, so here in green. So I would choose the one made with the lowest flow ratio. And the lipid formulation made with the stiff DSPC lipid, here I would choose the formulation made at the highest flow ratio. And that allows me to actually get particles of the same size and to compare apples with apples and not apples with oranges. So in summary, a better control over the mixing process in nanoprecipitation allows for fine-tuning of two key nanoparticle characteristics, which are the particle size and the size distribution. And the ability to fine-tune these particles in turn allows us to rationally design nanoparticle formulations for further cellular and in vivo experiments. Coming to the second point of our challenge list, let's discuss time. So most of the nanoparticle formulation techniques are, as you probably know, extremely time-consuming. If we compare this to the domains of drug discovery or target validation, which use high-throughput methods, the formulation department actually represents a real bottleneck in the early-stage development of nanomedicines. And for this, I'd like to have a closer look at what we call the top-down methods to really illustrate this issue. So in the top-down methods for making liposomes and lipid nanoparticles, you start with dissolving the lipid in an organic solvent in a round flask, and then you evaporate the solvent to form a thin lipid film on the wall of the flask. And then the thin lipid film is rehydrated with an aqueous buffer, and that results in the formation of large multilamellar vesicles. And these large vesicles then further need to be broken down into a smaller size, for example, by applying sonication or extrusion or high pressure homogenization or other methods. And while I just named 4 steps in this process, only the particle reducing, the particle size reducing part can involve up to 10 iterations. So all in all, this process is extremely time consuming, especially because each one of these steps is very labor intensive. Now, one way to increase throughput is to switch from a top-down method that needs all these different steps and iterations, to switch that to what we call a bottom-up method. So instead of first making the large particles and then breaking them down into smaller ones, the idea is to directly form nanoparticles of a defined size from the single building blocks, which in our case would be the single lipid molecules. And this is possible through nanoprecipitation, but the trick here is to do this in a microfluidic channel, as we determined earlier. Here we have a control over how the lipids self-assemble into liposomes and nanoparticles. So essentially, if we use a controlled nanoprecipitation technique, we can make liposomes or other nanoparticles of a defined size within 2 short steps. The first one would be dissolving the lipids in the organic solvent, and then the second step, we would perform the nanoprecipitation in the microfluidic chip, which takes less than a minute. So by reducing the amount of steps and the time involved in each iteration of the nanoparticle formulation process, we can reduce overall the overall time needed per formulation and thereby increase the throughput in the whole formulation development. Well, yes, but even the best designed particles made with the highest throughput fashion are not really of much use if we can't produce them consistently and allow someone else to produce them or reproduce them for you. And I'm sure you have all been in a situation where you or someone you know has had a fantastic result in an experiment and just wasn't able to reproduce that experiment, and you end up asking yourself, why is that? What can I do here? And so in my opinion, I actually want to say that low reproducibility is not itself a problem, but it's rather a symptom of a number of problematic factors in the nanoparticle development process. So let's look at some of these factors. First, the incumbent nanoparticle formulation techniques require strong technical expertise. There is always a human factor involved that makes transfer of protocols very difficult. Then secondly, as I already mentioned, I think twice now, there's low control over the particle formation physics, which makes it hard even for the same person or for one person to reproduce particles of identical quality. And then third, in a lot of cases, we don't actually pay enough attention to the particle quality itself, notably to the size distribution, for example. And further down the road, when we get into our cell and in vivo experiments, this can lead to misleading results and also, by that, low reproducibility. Now that we've determined some of these causes of low reproducibility, we should look at how we can get a good cure for each of these points. Now, one way of curing operator variability is to take out the art, if you will, or the human factor to take that out of the nanoparticle formulation process. And the simplest way of doing that is to introduce automation and software control, and also to reduce the steps related to each single formulation. Then devices such as a microfluidic chip can be used to enable faster mixing at low volumes and overall constant nanoprecipitation parameters to get better control over the particle self-assembly. And last, the ability to fine-tune your particle size while keeping the polydispersity low is key for more reliable results in vitro and in vivo. And this is also something that we can control, as I mentioned before, with a microfluidic technology. And in this slide, I'd like to show a plot of particle sizes and polydispersities of 5 times the same nanoparticle formulation, carried out by 6 different people with a different educational background. So here, basically, we had 6 operators. One was a student, then a technician, a professor. I think one was our CEO, and then another one was a secretary. And for the last person, I don't actually remember who this was. But essentially, they were all given the same lipid solution and a protocol, and they were asked to perform this nanoparticle or produce this nanoparticle formulation on the nanoassembler benchtop instrument by putting specific parameters into the instrument software and clicking the nanoparticle formulation solutions into the instrument. And usually, I know we like to show, or in scientific presentations, we like to show a fancy peak or a drop down to show a difference, but here the aim is actually to show the opposite. You can see in this graph that when you use an automated instrument that is software controlled, you can get the same results and achieve excellent reproducibility no matter who operates the system and what their educational background is. Okay, now that we've found a way to prepare rationally designed particles in a time-efficient and reproducible manner, comes the real challenge when you think of getting a commercializable product. And namely, that is, how do I translate a small-scale formulation into a large-scale production? So making a 1 milliliter in a test tube is not the same as making it in a small or large beaker, let alone making it in a large container of several liters. So scaling up a formulation is really not easy, and in fact, it often requires a complete change in the formulation methods and therefore a significant time and effort spent in process development. So with each step, each step up in volume actually, the reaction conditions vary, the concentration gradients change in the bulk, material yields are inconsistent, et cetera, et cetera. And so reducing all these variables in the equation will make Scaleup quite a bit more efficient. And you will have noticed that I really like to look at the microfluidics for that. And I'm going to take up this the scheme of this microfluidic channel here. And I showed that with this microfluidic device, we can actually have constant mixing volumes and constant mixing ratios. And this is the case when I want to formulate a small volume. So in this microfluidic channel, I could inject small volumes with a syringe into the mixers. And that's what we do with the nanoassembler benchtop instrument. But I can also feed larger volumes into this device by using a continuous flow pump, or continuous flow pumps, actually, in this case, we have 2. I can even put several microfluidic mixing channels in parallel, and thereby I can increase the total throughput of the device. And then thinking more in the industrial field here, I can add further steps after the nanoprecipitation, such as buffer exchange or concentration through diafiltration, for example, to get an all-in-one inline process for the nanoparticle production. And that is exactly what we do with the nanoassembler scale-up system. And this graph here shows you the formulation of one type of nanoparticle, a lipid nanoparticle formulation that was once made with the nanoassembler benchtop instrument, so at a small scale of 2 milliliters. And then in blue, we see the formulation made on a large scale-up system without having to adjust anything, really. We just made the exact same thing, just in a larger volume, in a system that had 8 microfluidic parallel chips. And if we look at the diameter and the polydispersity index here on the left, the quality of the particles doesn't change. And so this means that we can seamlessly scale up from the prototype stage to a large-scale volume and save a lot of time and energy in this process. Now, to conclude this whole thing, from this short webinar, I hope that I could make you, or I could illustrate 4 of the main challenges that we meet in the nanomedicine product development, which would be rational design, the time challenge, reproducibility, and scale up. And at the same time, I hope I was able to present the nanoassembler platform as a possible solution to these challenges. So going a bit more in detail, rational design, if we can get better mixing control and if we can allow fine-tuning of our nanoparticles, we can actually get a handle of this rational design point. If we can decrease the single steps for each formulation and have just shorter times for the formulations, we can increase the throughput and thereby meet this time challenge. For the reproducibility, if we take the art out of making nanoparticles, if we take out the human factor by automizing the instrument and introducing software control, we get excellent reproducibility. And by using the microfluidics and just putting microfluidic channels in parallel and doing this nanoprecipitation in this parallelized system, we can seamlessly scale up our nanoparticle formulation that we first made at a small scale with a benchtop instrument.